Hi, everybody. Let me show you what you're going to be doing on your lab tonight. Give you a few extra pieces of information that could help you answer some of those questions and show you how to submit it. The idea here is hopefully you can find some partners to work with. If you can't find one, that's okay. You can use the discussion board in Canvas to find some folks. But ideally, what we're going to be creating today is, let me show you my screen. What we're going to be looking at today is in here, in this atmospheric lab. You see where it says download the lab. The lab write-up is right here. The video will be up there after this is done recording. But basically, you can watch this video, and I'll put a link to here to make sure you've watched this video. If not, the instructions for how to do everything step by step are in slides 8, 9, and 10 down here at the bottom. And I guess I didn't put in a few of those pieces of information, so let me do that right now. In slides 8 through 10 at the end. So this week, basically, we just learned that several factors that create unequal heating of the atmosphere. And I'll show you some of those as we go back through this before I get you started here. But one of those big causes of unequal heating was clouds and being near coastal areas, things like that. So what I'd like you to do is you'll download this Google Sheet, this Google slide deck, and for slides number 2 through 7, these are the ones that you're going to be editing and filling out. So the first thing I need you to do is basically create a hypothesis. So your hypothesis is going to be in cloud-free coastal areas. So imagine an area where there's no clouds. The land surfaces or sea surfaces, so you choose one of those and type that in where the blank is, will exhibit a greater diurnal temperature range than either land seas or land surfaces or sea surfaces. So there's a couple of pieces of vocabulary there that you don't know yet, but I'm going to be showing them to you in just a moment. And we're going to be using the earth.nullschool.net to figure out what to do. But I just want to give you a heads up. This is kind of what your slide is going to look like. You're going to just be doing one slide a person and finding a coastline somewhere in the world that is cloud-free and measuring the temperatures for a 24-hour period near the sea and then right on the land as well. So I'm going to show you how to do that in just a moment. But first, I need to show you a couple of other pieces of information. So let me close my door really fast. Miss me? Okay, so what we basically finished talking about with the lecture was the atmospheric temperature controls. The greatest temperature control that causes the seasons on Earth is the angle of the sunlight. So direct vertical sunlight focuses that energy in a small area, creates things that are hotter. Take the same amount of energy and spread it over a greater surface area, like in the North and South poles. Since so much energy is diffused, things don't get as hot, all right? So those are the big controllers, but there's also 4 other kind of like sub-controllers of Earth's climate and places in the Earth. So think about California, right? The Central Valley is really hot, but if you go up into the mountains in the summertime, it can still be pretty darn comfortable and cool way up high. So how does that happen and why does that happen? So there's 4 other major factors that latitude does not influence, or other than latitude, I should say, that influences temperature. So the first one is the heating of land versus water. The second one is altitude. The third one is the geographic position, which I'll share in a moment. And then the fourth one is cloud cover, and that's what we're really going to be investigating today in combination with some of these other altitude combinations. So a big couple of things to understand is that land heats more rapidly and to higher temperatures than water. It's kind of like the sand analogy I made in the lecture. Sand heats up really, really fast, but it also cools off very quickly. Water heats up slowly, but it retains that heat for a long time and cools off slowly. So for example, if you have 2 places, let me get my pointy, like Vancouver in Washington and Vancouver in British Columbia and Winnipeg, which is in Manitoba or Saskatchewan, I think Manitoba. Winnipeg is in Manitoba. But in Canada, both of these are Canadian cities. Vancouver, very near the coast. Winnipeg, not near the coast at all. And so what you end up with is Vancouver's elevation is like 98 feet above sea level, but its maximum monthly temperature, and now this is in degrees Celsius, remember 0 degrees Celsius is freezing, 16 degrees Celsius is like 61 degrees Fahrenheit. That's how I always remember them. But it has like a 14 degrees Celsius temperature range. This is like your diurnal temperature range here. When you look at Winnipeg, all right, so Winnipeg has an elevation of like 748 feet, a max monthly temperature of like 20 degrees. The negative minimum monthly temperature it ever gets is about 18 degrees below zero in the wintertime. So the change between winter and summertime is pretty severe here. So it has like a 38-degree temperature range. I think I said diurnal earlier. I didn't mean that. Diurnal means a daily shift. This is a yearly climatological shift here. So depending on if you're near the ocean or far away from the ocean, that's going to control if you get warmer or cooler. What else do I want to say about this? Oh, I guess because you're in the land and the land gives off its heat so much more quickly, it gets very cold in the wintertime. Or if you're near that coastline, it stays very moderate. So in the summertime, when it's supposed to get hotter, the breezes cool you down from the ocean. And then in the wintertime, if it's supposed to be really cold, you notice they're about the same latitude. When it's supposed to get really cold, the sea brings in some of the warmer air and keeps it above freezing. So those are some big things. The altitude. High altitude, high elevations, generally way cooler than they are down in the valley. And if you've ever been to the Sierras hiking in the summer, you know that. And so here's a quick rule of thumb. It's that for about every 1,000 feet that you go up in elevation, the temperature drops by about 3 degrees Fahrenheit. That's just a quick rule of thumb. If you want to do in Celsius, it's about 10 degrees Celsius for every 1,000 meters that you go up. So here's Levitt Pass, this picture I took hiking a few years ago over by Levitt Pass, by Sonora Pass. So it's about 10,000 feet in elevation. Turlock's about 100 feet in elevation, so that's like a 10,000 foot change in elevation. So if I have a 10,000 foot change, and there's 3 degrees of change for every 1,000 feet, 3 times 10 is 30. This should be 30 degrees cooler up at the top than it is down in Turlock. So if there's 100 degrees down in Turlock, this should be about 70 degrees way at the top of Sonora Pass. All right, so elevation, the higher you go up, things cool down. Here's another great case study of that. In Guayaquil and Quito, both of these down in South America and Peru, and Quito, where's, are these both Ecuador? Oh, yeah, Ecuador. Forgot my geography there for a moment. So Guayaquil, if you take a look, is 7 feet above sea level. It's the red line there. So it has a maximum monthly temperature of about 27 degrees, minimum monthly temperature of 24 degrees, with a temperature range of 3. And you notice it's really doggone near the equator, so you don't have very much variation in their temperature throughout the entire year. Same thing is true of Quito. There's not much variation there. However, you notice the line is much cooler. So even though they're near the equator, they're at 9,300 feet up in the Andes. And so they have, you know, their maximum they ever get up to on average is about 16 degrees Fahrenheit or Celsius, which is 61 degrees Fahrenheit, and about 14 degrees for their lows. So that's only a 2-degree temperature range difference. But you notice, look at that. They are 20 degrees Fahrenheit apart in terms of their average climate for any given year. Pretty crazy. So they're really next to each other, but because Quito is way high up in the Andes, it's always much, much cooler, even though they're near the equator. So another one is the geographic position, kind of like we talked about Vancouver and Winnipeg. Winnipeg was far away from the ocean. Here in this case, we have Eureka and New York. Both of them are right next to the ocean. But what's kind of funny is Eureka gets these onshore winds that blow onto the shore. It's called a windward side. And so it gets these really steadying temperatures. If you look at Eureka, which is the red line right here, So its elevation is about 25 feet above sea level, 14 max, minimum is 9, so you get a temperature range of about 5 degrees. But in New York, the exact same elevation, but you have a way bigger temperature swing, especially in the minimum monthly temperatures during the winter time. And that's because in the wintertime in Eureka, the ocean winds, which are fairly, 55 or 6 degree waters, are blowing that wind into Eureka and keeping it nice and warm when it might be wanting to be cooler. In New York City, the same wind is blowing all of the energy of the ocean out into the ocean. So it's on the leeward side of the coast, we call that. So all that energy escapes out to the ocean, which helps make it much, much cooler and colder. So even though they're both on the ocean, the wind direction pushes that air off of New York City. And then another one is looking at mountains as barriers that prevent marine air from spreading inland. So Seattle, next to the coast, Spokane is still in Washington, but it's got the Cascade Mountains in the way. And so if you take a look at this, even though Spokane is just a little bit higher, so you'd expect it to be a little bit cooler, it has a greater temperature range than Seattle. And again, it's because Seattle lives right on the coast. And by the time the wind gets up and over the mountains of the Cascades, you don't have the same cooling and warming effects of the water over by Spokane. So the last one is cloud cover and albedo, and that's the big one we're going to focus in on the lab here. And basically what you need to know is clouds reflect incoming radiation during the day. So the more clouds you have in the sky during the daytime, the more of the sun's energy is going to be reflected. And when that happens, you have less energy hitting the ground, so it's cooler during the day. However, at nighttime, those clouds can act like a big, thick blankie. Remember, those water molecules absorb the outgoing infrared radiation. And so at nighttime, it keeps the Earth warmer if you have more clouds and if you have more water vapor in the sky. So in this picture of Death Valley, when I was there, the radiation is trying to get out, but it gets absorbed by the clouds or sometimes even reflected back down. So think about more clouds, the thicker the cloud cover, the thicker your blankie, the warmer the Earth's atmosphere will be at night. So here we go camping. It's great to have cloudy nights because it keeps things warmer, as long as it doesn't rain. So now here's the word I talked about at the beginning of the lecture, or the beginning of this lab thing, which is diurnal temperature patterns. So the diurnal temperature pattern is just the day and night swings. So what is the change in temperature in the day versus the change at night? That is a daily temperature swing, or what we call a diurnal pattern. All right. So kind of the ups and downs. We have cold in the morning, right as before the sun rises, really warm towards the end of the day. So check this out. The diurnal temperature range then is that difference between the maximum and the minimum temperatures for that day. And what's kind of interesting is if you notice, the maximum incoming solar radiation from the sun comes in at about noon, 12 o'clock. It's about when the sun is highest overhead, you have the most energy. But the maximum temperature doesn't happen until 4 or 5 in the afternoon, especially in the summertime like in Turlock. And that's because you have all this energy that keeps getting added and added and added to the system. And finally, by about 5 o'clock, 4 o'clock, or 5 o'clock in the afternoon, the energy leaving the system is greater than what's being stored up. So the temperature starts going down again, which is kind of cool. So kind of a lag time there. We can see this on most of the Weather Channel or Weather Underground. And so this is my weather station that you see right here. This is the diurnal temperature swing for one day here in Turlock. You can see the whoop up and then whoop down. The green line is the dew point or the humidity. And then here's another funny one. This is from my temperature gauge about March 25th, I guess it was, about a week ago. And you can see here, how might have clouds affected the diurnal temperatures of that day? This is one day, but you see the temperature goes up and then the clouds came over, less radiation, things got cold, then whoosh, clouds went away, temperature went up, clouds came over. And you can see down here at the very bottom in the yellow, I have something that measures the solar radiation coming in. And you can see how anytime it dips is when a cloud came over. And we see that when it dips, basically the temperature went down as well, which was kind of cool. And so the same thing happens with different surfaces on land versus water. So different surfaces heat up and cool down at different rates, like we said. Here's a picture of California in the summertime, like in June or July. You can see the Central Valley is just scorching hot, but you have the really cool ocean off to the side, and that really affects the daily different temperatures, all right? So this is a cloud-free afternoon, what you're seeing here. If you put clouds in the picture, that might make things a little different. So if you had an overcast day, you're not gonna have as big of a temperature swing. You're gonna have cooler days, but warmer nights, as opposed to a clear day. So in a clear day, you have less clouds, more radiation can escape at night, and so it cools down much more quickly. Think about all the foggy days we've had in the Central Valley. When it's a foggy day, it doesn't get much different. Then it's like 49 degrees for the high and 45 degrees for the low. There's not much of a diurnal range there. All right. So what we're going to be doing on this lab is focusing on where there are no clouds. And we're going to be focusing on areas that are near the sides of the ocean, or coastlines, I should say. So near the ocean and cloudless. So here's what you're going to do. You download your Google Slides, and basically these are the slides. You've already done your hypothesis. So I'm going to show you how to make this slide. You only need to make one of these. If you work with a group, you can share the ideas with each other. You can share, oops, here it is. You can share the slide deck with one another, and then each person just contributes one slide. Working with a group might help you answer some of the questions more easily later on. So once you hear the sample data slide right here, this one was compiled by Noah. If you want to create your own slide, just right click on the slide over here where it says number 3, and it says duplicate slide. I'm going to duplicate slide. And now I have an exact copy. These ones are exactly the same. And I'm going to change this, and I'm going to go down by Brazil, I think. I'm going to do the Brazil coast. I'm going to put my name by who compiled it, so me. Excuse me. And so just like we did last week with some screen captures, you're just going to have to make one screen capture is all. So I'm going to delete this one, and I'm going to delete these because we're going to be entering in the data into here. And I'm going to delete these. So basically, and if you get lost, remember all the instructions are on page 9, 10, and 11 down at the bottom here. You need to find on earth.nullschool.net, if I can find the right tab here, you need to go here, and it'll open up and give you this general picture here. What I've clicked on, actually, let me restart. So I'll go to, let's just say you go to earth.nullschool.net. This is what it looks like if you were to first log on. So what we want to do is we want to zoom into a coast, and we want to find a place where it hasn't been too cloudy in the last few days. What this is showing us right here is just the wind. What we're going to be interested in is in the temperature, but we want to find an area that's not cloudy. So the way we find it that's not cloudy is if you click on right here where it says Earth in the bottom left-hand corner, this will pop up. And then I want you to click on TCW, Total Cloud Water. And the total cloud water will show up where there is, it's white wherever there's clouds. So if it's dark blue, that means there's no clouds. If it's white, that means there's clouds in the area. So all you have to do is just go along around the world, anywhere in the world that you want, and find a coastline that hasn't had clouds in more than a day. So how do you know if it hasn't had clouds in more than a day? Well, you'll zoom into an area. There's still some white stuff right there, so I know there were clouds. But if you click the controls where it says now, that's your current conditions. But if you click the one that has 2 little arrows pointing backwards, right there where it's highlighted, that means it goes back in time 1 day. So I'm going to click on that, going backwards 1 day, and then I'm going to go back to now, and I can see how the clouds have changed. And if I zoom in, like right in there, I'm going to think about this spot. I'm just going to put a green dot right there so we can see. That's here's now, here's yesterday. So this area looks like it's been cloud-free for 24 hours. That's good. So now what I want to do, once I found my cloud-free area, I'm going to go back over to here, and I'm going to click on where it says overlay. I'm going to click on the word temp. So I click on temp, and now the temperatures pop up on the screen. So what you're going to want to do is you're going to want to find the temperature, and hopefully you can do it in Fahrenheit, and you just click the C to change the C to Fahrenheit. You're going to click somewhere fairly near the coast. All right. If you want to zoom in more, this is about as far as I can zoom in. So I'm going to choose this area. There's my green dot. I'm going to print screen. So this is the first thing I'm going to do. I print screen. I'm going to go over to my slide deck, the example here. So if I can find it, there it is. Here's my sample slide. I'm going to Control V. So I've just pasted my sample in there. My circle is in there. That's totally fine. And then what I also like doing is just copying the URL up here, so then we can find it later on. Like we can zoom right into what you were looking at later on if we need to. All my tabs are being covered by the Zoom thing. All right, so I'm gonna just paste in right up here, just really quickly, the URL. So now all we have to do in these bits is find the temperature of the land area and the sea area for 1, 2, 3, 4, 5, 6, like for 24 hours. So I think it goes in 6-hour increments. 6, 7, 8, 9. Yeah, something like that. So basically fill the data table up. It goes in 1, 2, 3-hour increments. Okay, that's what it was. I couldn't remember. So we're going back to Earth. And now that we're here, click on Now. So there we are on Now. And now what's kind of fun is we can see here's our time, the local time, 1400 on 3/31/20. So that's be 2:00 p.m. local time on March 31st, 2020. So I'm going to go back to the lab here. And for this first one, I'm going to write down, very much like you see in this one, I'm going to say 3/31, and then the time was 1400 hours. Oops, like this. And then my land temperature, so I'm going to go back over to here. My land temperature at this spot was 77.7 degrees. So I go back over to here. Oops, if I can find the right doggone one. And put in 77.7 degrees Fahrenheit. Then the next thing you do is you go back to here, and you're going to use the one arrow going backwards, and that'll go backwards 3 hours. So I'm going to click that, go back 3 hours. Hey, look at that. So now it's 3/31, but at 1100 hours. So I'm going to type in here 3/31 at 1100 hours. All right. And I think in this case it was 84.8 degrees. So you're going to type in 84.8, and you're just going to keep doing that until you fill in all of these. It'll be a 24-hour period by the time you get down to the bottom. So you just go back and click the back arrow, another -3 hours. And so here it is at 0800. Click it back again. Here it is at 0500. So make sure you write down those temperatures in the grid. Once you get the land temperatures done, then you just need to go off onto the coast of the ocean here, boop, like that. So now I'm on the ocean side of the coastline. Go back to Now and start from where you started with the other one, write in the temperature of the sea at 1400 hours, and then write in the temperature of the sea at 1100 hours, then the temperature of the sea at 800 hours. So to give you an idea of what that looks like, maybe, All right, here's the example slide that Noah provided earlier. He did one in Australia, so that was kind of cool. So all you have to do is once you get your data table assembled, you need to take the total diurnal range. So what was the maximum temperature minus the minimum temperature. So find the highest temperature on there, subtract it from the lowest temperature, and that'll give you your temperature range. And then the same thing for the sea. What is the difference in sea surface temperature versus, or the high surface temperature for the day versus the low temperature for the day. So once you get those done, what I need you to do is create like a sample results slide. Hopefully, if you worked with some other folks, you can kind of collaborate and put all of their data ranges right in here. If not, we'll figure out a way to put them together as an entire class, so we can compare and see what it's like all around the world. So once you get down through that's kind of the sample results slide. You might need to create your own copy for that as well. But once you have all that done, there's a little discussion and analysis here. So you can tell me, does your data support your hypothesis of what was going to be hotter or colder, the land versus the sea? What might have been a source of error? If we did this again, how could you improve it? And then what were you surprised by? What did you wonder? So kind of the notice and wonders we've done. So then the conclusion, based on your results in a cloud-free coastal areas, blank surfaces will heat up and cool down more fast or more than other surfaces. So land versus sea. If you want to add something, however, go for it. And then the last little bit here, and I got to erase this part because we don't need to do this one. But the reflection on learning. So in this week's lab, we saw hopefully that all these things heat up and cool down at different rates. So do you think all land surfaces heat up and cool down at the same rate? Or do some land surfaces heat and cool differently? So here's an example of Turlock and Modesto in Stanislaus County with the coast ranges and the foothills there. So basically try to take what you've learned about the land and the sea and some of the other things we've talked about today and give your answer for this. That's it. Once you're done, take this link. You can send me the link with your own slide deck and you're good to go. And don't forget, file, make a copy, and once you make that copy to your drive, you'll be able to turn that in, no problem. So let me know if you have any questions. Just the one slide is all you got to do.